Welcome to Ready to Derive. If you haven't yet watched the prequel to this video, called The Shapes of Curves and the First Derivative, you might want to do so first, as much of what we will do in this video builds on the concepts and problems developed in the previous one. In particular, we will explore how the second derivative can help us fine-tune our analysis of a function and our ability to graph it more accurately. We will also cover the second derivative test, which is a pretty cool alternative to the first derivative test. So without further ado, let's get started. So in this slide, we're going to begin with an introduction by looking at some real world contexts and the shapes of curves that they describe. So at each stage here, you might want to pause the video and try and predict what the curve is going to look like. So let's take the upper left-hand corner. The number of people with the flu is rising, but at a faster rate than before. And hopefully you would draw something like this. A curve where the tangent line seems to be increasing in slope as you move from left to right. Now, what about the upper right corner? The child's temperature is still rising, but at a slower rate than before. So you're still going to have what we would call an increasing function, but notice that it curves in a different way because the rate is slowing down. The slope of the tangent line is becoming less steep. What do these have in common, both of these? Well, in both cases, there is a situation where f is increasing. And what that translates to is that, as we know, because of increasing functions, it means that f prime is positive for both of them, but in a different way. And what about the bottom left-hand corner? Coffee temperature is decreasing, but at a slower rate than before. Sort of predicts something like this. So the temperature drops pretty dramatically at first, as we know happens with hot drinks, and then kind of slows down. The rate at which it's cooling slows down. And that's a decreasing function. And what about the bottom right? The height of the ball is decreasing, but at a faster rate than before. Hopefully you would get this curve. What do the bottom two curves have in common? In both cases, f is decreasing, so that f prime x is less than 0. So, but there is a commonality if we look at the columns. So let's look at the first column with the two curves that seem to be what we would say opening upwards. But let's think about what is actually going on and think about the slope. Let's have a look at the slope of tangent lines as we move from left to right on this function. The slope of the tangent line, let's predict that this approximates. Maybe that's about a half, that's 1, and that's 2. We see that in this case, f prime, so the value of the slope, seems to be increasing as we move from left to right. Now let's come to the one down bottom left, and let's predict, let's approximate, sorry, that looks about -2, that looks about -1, and that looks about -0.5. So I know that the value seems, the magnitude of the value, or the absolute value seems to be getting smaller, but in fact, f prime is still increasing as you go from left to right. It's just increasing from -2 to -1 to -0.5, so it's becoming more positive. So in both scenarios, in the first column, we have a situation where f prime is increasing. Well, if f prime is increasing, that means any function that's increasing, we know its derivative is positive. So if f prime is increasing, the derivative of f prime, f double prime, has to be positive. Similarly, let's look at the right-hand column, and let's make some approximations. What's happening to f prime here? So why is it slowing down the rate? Well, the slope here looks like it's about 2, approximately 1, approximately half. Clearly, the value of f prime is decreasing as we move from left to right. Is that also true here? Well, we got to kind of, in a negative sense, this is -0.5, -1, -2. So it's becoming more negative. So f prime, again, is decreasing as we move from left to right. So in this case, in the right-hand column, we see that f prime in both cases is decreasing. Sorry, let me use this one. And then that means that the derivative of f prime is less than 0. So these two have the left-hand column, these two curves have a very similar property. Even though one's increasing and the other is decreasing, these are said to be curves that are concave up. So concave up, concave up. Notice that they look like sort of, cups that are facing upwards. Whereas in the right-hand column, we say that the two curves are concave down. So this is concave down. And we'll explain more in the next slide. So let's summarize what we found in the last slide. So again, we have two scenarios here. We know that we can use the first derivative to determine if a function is increasing, but the problem is we don't know if a function is increasing like this or like this. Both of these functions are increasing, but in different ways, and that's where the second derivative comes into play. So we found that if f double prime of x is greater than 0 on the interval, i.e. the value of f prime is increasing, remember f prime being the slope of the tangent line is increasing, then we say that f is concave up on that interval. And a nice way of remembering this, well, first of all, some people say, well, concave up rhymes with cup. So the shape of it is something that could, looks like a cup or could hold water in it. Another way that people remember it is they do a little smiley face with two eyes, two plus signs for eyes, indicating that f double prime positive means it's concave up. On the other hand, we still have the increasing function, but if f double prime is less than 0, which means that f prime, here we go, f prime, the value of f prime is decreasing as we move from left to right, we say that the function is concave down on that interval, and down rhymes with frown. And then the image to use for that is you do a little frown with two negative signs indicating that the second derivative is negative. And another way to do it is if you're thinking about the curvature, sort of as this curves, it sort of opens up in a way that the arrows are pointing up, whereas here, just consider the arrows being like little normal lines, perpendicular tangent lines. They're pointing down, hence concave down, which rhymes with frown. So while there are some curves for which concavity never changes, take for example a parabola. So this parabola in particular is concave up always. More often than not, concavity just does change. And so let's look at a few examples. So here we have what appears to be the function is concave up at first, and then switches to concave down, continuing on there. So if we know about concavity and where it changes and how it changes, we can more accurately sketch graphs of functions. Here's one where it's concave down at first, and then somewhere it switches to concave up. And where it switches is a very special point I'll reveal in a second. I like to think of, in this one, I like to think of, imagine you were skiing down this slope. At first you're going slow, then you'll start to speed up, and then at some point, the special point where the concavity changes, you'll be speeding up, you'll be going the fastest at that point, and then after that point, you suddenly start to slow down. So that special point is where the concavity changes. And here's one other one. Again, we have concave up here, suddenly somewhere along here it changes, and then the curve becomes concave down. So that special point, without further ado, is called an inflection point. So wherever that occurs, sometimes we use IP to abbreviate it, it's called the inflection point, and that's where the curve changes concavity. And if you look at if you look at inflection points, if you think about it, if this is changing from concave up, so if f double prime is positive and then f double prime becomes negative, it does make you think that at the inflection point, then surely that f double prime has to equal 0. How can it go from positive to negative without passing 0 on the way? And that would be true for the first two examples. But for this one here, the third example, if you notice, there's a vertical tangent line there. So that means f prime is undefined, which means f double prime is also undefined. So that leads us to another important conclusion, is that at an inflection point, either f double prime is 0 or f double prime is undefined. That's the only way in which a curve can really change concavity. So let's look at the steps for determining intervals of concavity and inflection points algebraically when you don't have a graph in front of you. So step one would be to find the second derivative of the function, as everything hinges on the second derivative. And I'm just going to give you a simple function. So this is obviously the second derivative of a polynomial, a degree 4 polynomial. So this is a simple example to work with. And then you find where f double prime is equal to 0 or undefined. Now, don't confuse these with critical points, critical values. Critical values are where the first derivative is 0 or undefined. For the second derivative, they don't really have a special name, but they are kind of crucial points. So you would always begin probably by factoring, if possible. And then in this case, there's no value of x for which it's undefined, so you would just set it equal to 0, and you would come out with x equals 0 or x equals 2. And those are points about which it's possible that the curve changes concavity, but not guaranteed. So in order to find out where f double prime is positive or negative, you might think to yourself, well, why don't I just solve and find out when that inequality is greater than 0? That is hard to do algebraically, and it's much easier to do this number line analysis. So what you do is you take your values, 0 and 2, and that's where f double prime, we know that f double prime is 0 here and 0 there. So that's possible places where the concavity might change. And then you do, you test, as we did for the first derivative in the video on shapes of curves and the first derivative, you pick test values in the intervals you're interested in. And so a test value to the left of 0 might be -1. And you take -1 and you plug it into the second derivative function. And if you did that, you would get, I'm going to take the factored form, you would get -1 times -1 minus 2. And it would be a negative times a negative, it would come out to be positive. Similarly, for this interval, so if it's positive, that means the function is concave up in that interval. In this interval, we would take a test value maybe 1, and we would find out that if you plug that in, you'll find out that that comes to negative, and also take a test value here, maybe 3, you'll find that comes out to be positive. So that's what's happening with the sign of f double prime. So what does that mean exactly? Let me just take these arrows away and let's translate that. What does this mean about the function itself, about f? Well, if f double prime is positive from -infinity to 0, the function is concave up, and then negative, concave down, and then up again, concave up. And since concavity changes at 0 and at 2, they're both inflection points. So we just might make a note of that. That's an inflection point, and so is that. And you are often asked to justify your responses to questions that ask for concavity, etc. So you would say f is concave up on those intervals because f double prime is positive over these intervals. You'd say f is concave down on 0, 2 because, of course, f double prime is negative over this interval. And finally, you'd identify the inflection points at 0 and 2 because f double prime changes sign at these values. So for our first practice example, we're going to revisit a function that was investigated in the video called The Shapes of Curves and the First Derivative. So I'll do a quick review of what we analyzed there using the first derivative. So first derivative would be this, and then we had to look for the critical values of the first, by using the first derivative, we'd set that equal to 0 because it's never undefined, f prime x, it's a quadratic, so it can't be undefined. But if you factor that and set it equal to 0, you will get the critical values being x equals -1 and x equals 3. And then in order to analyze with the first derivative intervals of increasing and decreasing and looking for max and mins, we filled in this number line analysis. As a reminder,
to figure out the sign of f prime, you just take a test value that's, say, in this case, to the left of -1, so you could plug in -2, and you plug that into f prime. Not the original function, you're not looking for a y-coordinate, you are looking for the sign of f prime. So let's take that away, and that was the number line analysis we got. And then we interpreted that. What does this tell us about f? What f is doing? Well, f prime positive means it's increasing, f prime negative, the function is decreasing, and here the function is increasing again. That also gave us some information, because if the function goes from increasing to decreasing, we know we have a local max here, and we also therefore have a local min here. And so in that last video, we actually graphed, we sort of said, well, with the functions increasing up until -1, x equals -1, and if you plug -1 into f, you will get 9 now as the y-coordinate. So we know we have a local max there, then it starts decreasing, and then we have a local min at x equals 3, and the y-coordinate of that is -27. And so in the last video, we would have just connected the two, but the thing is that what we would like to know if there is an inflection point there. So we do the second derivative now, and we find the zeros of the second derivative. So the zeros of the second derivative, well, if you set that equal to 0, then x equals 1. We bring up our number line, we plot 1 there, and then we look at test values, but now we're going to plug it into f double prime. So if you pick a value in this region, you could pick 0, f prime of 0 equals -6. So that's negative here. And if you pick a value here, so say 2, f prime of 2 would equal +6, which is greater than 0. So now we have information about the concavity. So we know that if f double prime is negative, it's concave down. If it's positive, then f is concave up. And we know therefore that at 1, because the concavity changes, at x equals 1, we have an inflection point. And if you plug 1 in to the original function, you can get that y-coordinate. So now we can locate the inflection point, which comes out to be at 1, -7. And why that matters is because then we can see that the curvature, the concavity is going to change. So if you look from here all along here, it's concave down, certainly is. And then at that point, 1, -7, it becomes concave up. And then we create a pretty accurate picture of the function. So for our second practice example, we are now revisiting the second practice example from the aforementioned video on shapes of curves. So once again, let's see how far we can get with the first derivative. So that is the first derivative by the power rule. And if we set that equal to 0 and solve, and also observe that for f prime, when x is 0, f prime is undefined, we actually we end up with 2 critical values. So again, to see the details, you might want to revisit the previous video. But those are the critical values. They make x equals 0 makes f prime undefined, and x equals 8 makes f prime equal to 0. So we get the number line analysis going, and we make our conclusions that f is decreasing here, increasing, decreasing, and then therefore we have a local min at x equals 0 and a local max at x equals 8. Once again, you can plug 0 and 8 into the function, into f of x, to get the y-coordinates, and then we just graph. So we have, here we go, we have the minimum at 0, 3. To the left, the function's decreasing, then after, between 0 and 8, it's increasing, and then we have a max at 8, 19. So what we talked about in the last video is how do we know that the function is decreasing, but how do we know if it's decreasing like that, or as with the blue curve? And what about here? How do we know on this side whether it's increasing like this, or maybe increasing like that? So that is where the second derivative comes into play. Let's erase that, and here's the second derivative. You could prove that to yourself using the power rule again. And we see that with the second derivative, it seems like the only value for which it's undefined, it will never equal 0, but it's undefined at x equals 0. So that is what we are going to put in the middle. That's the only value of x about which it's possible that the concavity will change. And we take a value to the left of that, and we see, so pick a value, -1. If you plug that in, it will come out to be negative. Now, interestingly enough, if you pick a value to the right, so for example, 1 is easy because that cube root of x to the fourth is a bit of a nightmare, but if you pick 1, it comes out nicely and you get -8/3. So it continues being negative. It continues being concave down. So in fact, what I've drawn to the left of x equals 0 is correct. And to complete this picture, notice that 0 is not an inflection point. The concavity doesn't change. The function remains concave down, and that's why we know we can connect it like this. And so we obviously, if we had tried to do something concave up like this, we would have actually ended up having to introduce a new inflection point. Otherwise, there would be no way of connecting those two pieces. So that is the final analysis of the function. So before we conclude with a final example, we have to be introduced to the second derivative test, which is pretty cool. The first derivative test helps us to determine if x is a critical value is a local max, min, or neither. And the second derivative test also can be used to determine if we have a local max or min. So let's consider this scenario. If you think about it, if you have a local max, well, what do we know about at that local max? We know that f prime of c equals 0. We also know, look at the shape of the curve, that it's concave down. So if it's concave down, that must mean that f double prime of c, let's call this value c, f double prime of c has to be less than 0. So here's a neat little result. If f prime c equals 0, and f double prime of c is less than 0, then f has a local maximum at x equals c. So you don't even have to do a number line analysis with the first derivative. You can just bypass that and move to the second derivative. And in this case, when we have a local min, if we have a local min, sorry, we're just going to keep consistent. So here's a local min, try and use the same color. And what's true for local min? Well, sure, f prime c equals 0 again, right, if this is c. But now for a local min, the curve is concave up. That's the only way it could be a local min, which means that f double prime c is greater than 0. So here's the second part of the second derivative test. So what happens? What other scenario is possible? Is possible that you get f prime c equals 0 and then f double prime c equals 0. Well, if you get that, unfortunately, there is no conclusion, and you'd actually have to go back and do the first derivative test to check. So that's the only caveat for the second derivative test. It's really neat when it works, and it's inconvenient when it doesn't. So for the final practice problem, we are actually going to revisit the function in practice 1, and we're going to check out those critical values and see if we can determine whether they are local max or mins using the second derivative test. So step 1 is find the values of x for which f prime of x equals 0. So there's the derivative function. When we set it equal to 0, factor and solve. Recall we got x equals -1 and x equals 3. So those are the values at which f prime is equal to 0. And now for the second derivative test, we just have to plug those values in to the second derivative, which is 6x minus 6. So plugging in -1, we would get 6 times -1 minus 6, which equals -12, which is less than 0. So therefore, the second derivative less than 0 means that it is concave down at x equals -1, which means we have a local max there. And now if we plug in 3, 6 times 3 minus 6, 18 minus 6 is 12, which is positive, which means that the function is concave up at x equals 3, which means we have a local min. So the last thing you would do is conclude invoking the second derivative test. So by the second derivative test, f has a local max at x equals -1 and a local minimum at x equals 3. And that is pretty efficient and saves us having to do a number line analysis using the first derivative.
And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.